Good evening, everyone. Hope you're having a good evening. Let's go ahead and jump into our next lecture. Tonight, we're going to talk about air resources. This is the first of, I believe, two lectures on air resources. This one's going to be some of the basics, and then we'll have some local case studies next time when we get together. But for now, let's talk about the atmosphere, which you're probably familiar with since you're inhaling it right now, I assume. And you should be aware that what you're inhaling is not necessarily the entirety of the atmosphere. You're specifically looking for a specific component. You're looking for oxygen and you're exhaling carbon dioxide. Neither one of them is the most common element in the Earth's atmosphere. The most common element is nitrogen, and it makes up more than 3/4 of the Earth's atmosphere. Yes, I may very well test you on that because I want you to remember the majority of the atmosphere that you live in is not something that we utilize to survive. We use oxygen, which is the second most common element in the Earth's atmosphere. But again, it's less than a quarter of the Earth's atmosphere, it's only 21%. There's argon, which is less than 1%. There's carbon dioxide, which is a tiny fraction of the Earth's atmosphere, 0.04%. Now, we're going to be talking about carbon dioxide actually quite a bit later in the term. But for now, realize that it is a very small percentage of the atmosphere. That doesn't mean that changes in the amount of carbon dioxide can't have dramatic effects, but it does mean that carbon dioxide is not a huge contributor to our atmosphere today. And then finally, there are trace amounts of other things like neon, helium, methane, krypton, and hydrogen, as well as water vapor. The one I really want you to keep in mind is oxygen. That's the one that we're using, that's the one we depend on. But also probably remember that the most common element in the Earth's atmosphere is nitrogen. Now, this has not always been the case. When the Earth first formed, it didn't have much in the way of oxygen in the atmosphere at all. In fact, Earth probably was covered by a variety of gases that didn't include oxygen. And if you looked at the Earth's surface for billions of years, there was incredible tectonic activity. There was volcanism, maybe not billions of years, maybe hundreds of millions of years. But still, there was a lot of volcanic activity, which then is kicking materials from the Earth's molten surface into the atmosphere. And then what you're going to have is eventually some of that is going to condense and it's going to precipitate, and you're going to start the development of oceans, which are made of water, hydrogen, and oxygen. And this is where a lot of the oxygen was present, was in the oceans, not in the atmosphere. So I'm not saying oxygen wasn't present on planet Earth. Atmospheric oxygen was practically nil. There just simply wasn't a lot of it. What oxygen there was locked up in the oceans. What was in the atmosphere, and I want you to remember this because it's so different from what I just told you. Um, excuse me. What was present in the Earth's atmosphere is carbon dioxide, which again has oxygen in it, but as carbon dioxide, which has up to 200 times, at this point in time, up to 200 times more abundant in the Earth's atmosphere than what we see today. So, yes, carbon dioxide is a very small fraction of what we have today. In the past, in the distant past, prior to the origins of life on the planet, carbon dioxide was much more prevalent in the Earth's atmosphere. And carbon dioxide, as we're about to talk about and we'll talk about again, is a greenhouse gas. And so, what it is doing is maintaining a high temperature on the surface of the Earth. So, you had volcanic activity, lots of carbon dioxide, very, very high temperatures, and so on. This is what the early Earth was like. But that carbon dioxide is important. And if you remember your photosynthetic pathway, which we have talked about all term long, you can understand why, because carbon dioxide was necessary for the appearance of the earliest living things on the planet. And these are known as cyanobacteria or blue green algae. And they first show up quite some time ago, and they produce oxygen using photosynthesis, right? We've talked about photosynthesis. Plants will take in, or organisms with chlorophyll will take in carbon dioxide and release oxygen. So, as these organisms develop and start sucking down all the carbon dioxide, all the rich amounts of carbon dioxide in the Earth's atmosphere, they start polluting the atmosphere with this stuff called oxygen, and it dramatically changes the Earth's composition. And this happened starting around 2.33 billion years ago in an event called the Great Oxidation Event or the Great Oxygenation Event. And in this case, I will use those two terms interchangeably. So if you see one or the other of them on the exam, they both mean the same thing. So treat that accordingly. But atmospheric oxygen on the Earth first became abundant enough to be preserved in the rock record about 2.33 billion years ago in an event called the Great Oxidation or Great Oxygenation Event. And this is when we start seeing oxygen showing up in noticeable levels in the Earth's atmosphere. And once oxygen started being produced, it started taking off because the organisms producing it started taking off because there was so much carbon dioxide in the Earth's atmosphere, because that's what these cyanobacteria needed in order to survive. And the atmosphere was so rich with it that these guys just went nuts. And it took about 10 million years, which sounds like a lot to you and me with our short time span perception, but geologically 10 million years is not very much at all. And it took about 10 million years for the oxygen to be so abundant in the Earth's atmosphere that it started causing chemical weathering of rocks at the surface. And this is how we have the dates on this. We actually still see the rocks that preserve that ancient evidence of the early stages of chemical weathering or oxidation. And what you're looking at here is those red bands of rock that are called banded iron formations or BIFs, not to be confused with other BIFs that are out there. And what you essentially see is these rocks have been exposed to enough oxygen that they are oxidizing, essentially rusting. And that's what's going on with these rocks. And this, in the rock record, is when you first see that appearing. So this is how we know when it first happened, because oxygen is required for these minerals to form in this manner. So the appearance of banded iron formations, or BIFs, is what informed scientists about when oxygen first becomes noticeably prevalent and abundant in the Earth's atmosphere. Now, it was a long geological time later before oxygen reached the levels that we have it today, where it's a little bit under a quarter of the Earth's atmosphere. And this happened with the development of a different kind of organism known as a cryptogam. And cryptogams are organisms that, as we've discussed with asexual organisms, they reproduce simply by growing spores and then releasing those spores, which settle somewhere else and then lead to these forms spreading. And as these formed on the surface, on the dry land surface, and started colonizing the terrestrial ecosystem, that's when you see oxygen reaching the levels that we see today. And because they are reproducing asexually, they're able to spread relatively quickly, which means they're able to release oxygen relatively abundantly in increasing numbers until they change the composition of the atmosphere, and oxygen reaches about the same percentage in the atmosphere as we have today. Now, again, the Great Oxidation Event or the Great Oxygenation Event was 2.33 billion years ago, billion with a B. This event is a mere 420 to 400 million years ago, much, much, much more recent. So you can think about how that's an enormous span of geological time where we didn't have as much oxygen in the Earth's atmosphere as what we're used to dealing with today, that we depend on today in order to survive. And this has recently been demonstrated in this paper that was published in 2016, so not quite a decade ago. So it's not quite as current as some of the papers that I've given you, but still it's relatively recent. And this is what's talking about the ages I just gave you when oxygen reached the more or less the levels we see it in the atmosphere today. And I want to emphasize this because this means it wasn't until around then that all of the biological processes we've talked about in terms of trophic levels, in terms of producers and primary consumers and secondary consumers, all of that takes oxygen and carbon dioxide. But the producers are, in addition to producing energy, they're producing oxygen. And from there flows the rest of everything that we have been talking about for the entire term. All of the ecosystems we've discussed are getting their energy from the sun, and they are thriving off that interplay between oxygen and carbon dioxide through the process of photosynthesis. But first, you need the plants, then, you need the oxygen released into the atmosphere, and then you have all of these organisms dependent on on that oxygen, and then exhaling carbon dioxide, which the plants then depend upon. So all of these wonderful biological nets start after you first see those cryptogams expanding and releasing oxygen into the atmosphere to about the levels we have them today. Okay, so that's the background on the atmosphere. Let's look at the atmosphere today. And these are different levels of the Earth's atmosphere. And I will say right up front, hold this dear. I'm only going to test you on two of these. The bottom two, the troposphere and the stratosphere. Yes, there's a mesosphere, a thermosphere, and exosphere. No, we're not going to talk about those because we're already past the halfway point on this class and we've got to wind things up. But let's go ahead and start by talking about the troposphere, which goes up to maybe about 15 kilometers above the Earth's surface. And pretty much you have likely spent your entire life in the troposphere. You might, in some cases, if you're flying and your pilots hit turbulence and they decide to try and get up and over that turbulence, they might edge on up nearer the stratosphere, which is the next layer up. But generally speaking, if you were traveling and seeing stuff like this, or you're here on the ground, you're in the troposphere. Chances are excellent that the majority of you have spent your entire life and will spend your entire life in the troposphere on planet Earth. Now, the troposphere is where weather takes place. This is where, when you think of weather, this is where it happens. It doesn't happen in the atmospheric units above us. It's strictly a tropospheric event. And this is also where the water cycle takes place. And this is what we're going to talk about in a different lecture, so I won't go into it too much here. But the basics are that you have surface moisture, whether it's in the rocks or it's in the ocean or whether it's in lakes and rivers and so on. And as that is heated, it evaporates, it goes into the atmosphere as a gas. As it condenses and forms clouds, eventually it precipitates and falls back to the earth as either rain or snowfall. So you have evaporation, condensation, and precipitation. Those are the basics of the water cycle. And again, we will be talking about that in a lecture coming up in about a week. So, but this is not the water lecture, that's a different lecture. But this happens in the troposphere. And so when you think of beautiful vistas like this with threatening clouds overhead and beautiful rainbows and all this lush life you see here, all of this is a tropospheric manifestation. You don't see this in the other layers of the Earth's atmosphere. This is also where we get atmospheric convection, and this is extremely important for the temperatures that we now go through here in Southern California and literally all over the world. What you do is you have the development of low pressure systems and then high pressure systems. As the sun heats the ground, it forms convection currents of atmosphere that move up, they lose their heat, and then they circle back down. And so the air is then warmed by this and then it drops and so on. You have this cycle. Further, you have warming, you have convection, you have cooling, you have decrease, you have warming and convection again over and over and over. And while this is a generalized diagram of how it happens, this is even more generalized, but basically you have warm rising air, and this creates an area of low pressure. And then as it cools, it sinks back down, it becomes more dense, and this creates areas of high pressure. This is a diagram of planet Earth, and it's showing these cells, these convection cells, and you can see them over here. So right here, do you see how this is cycling up? And this one is yeah, give me a break. This one is cycling up, and this one is cycling up. Those are areas of lower pressure where the air is rising. Okay, and you can note those here. And then you have areas of high pressure of sinking air where the air is convecting back downwards towards the planet. And you'll notice here that that one high pressure system there in the top that's labeled high, that's crossing a desert area of Africa known as the Sahara Desert. And so there's a reason that you have such persistent high pressure there. It's because of global atmospheric circulation, it's because of these convection cells that ring the planet. This is another diagram showing the same thing. I picked this one, somewhat the same thing. I picked this one because now it's showing more North America as being the focus, since that's where we live. I figured you'd be interested. But hopefully you can see that down there just to the south of Baja and in our area, the downward flowing air circling downward is what's creating a high pressure system, which is making our clear skies and our deserts much more common than they would be in lower pressure systems with upward flowing air. Okay, so a lot of where we live and a lot of the weather and the climate that we enjoy is a direct consequence of these convection cells and these atmospheric movements. But it's not necessarily an absolute because the earth is moving, the oceans are moving, and so things can get a little more complicated. For example, you might find diagrams like this that will show areas of high pressure off of either coast, which you would expect at this latitude, but then you can see how the oceans and the continents are reacting to that in different ways. And because the earth is moving and because the oceans are moving, these things do have some variability. And you probably know this if you watch the weather, and weather people will talk about how there's a new high pressure system moving into the area or the previous high pressure system is breaking down. It's because these are generalized concepts of how things work. The convection cells are pretty well documented, but within those, there is room for variation. And so there's room for these changes in weather that we've even been experiencing recently. Now, part of the reason for that is that the Earth is not completely flat. And it's not all one thing or another. It's not all water or all land. You've got different features, terrestrial features, marine features, and how the air moves over those is going to be different. And you also have on land the development of things like mountains and hills and ridges that are going to have an effect on the air patterns and consequently on the convection cells and how the weather drives itself. Because, as we've discussed, and as we will discuss again, California lies right here along the boundary between two plates, the North American plate over there on the right and the Pacific plate over there on the left. And the San Andreas Fault is the join between those two plates. Okay? And so the North American plate is pretty much more or less moving down towards the southeast, while the Pacific plate is moving up towards the northwest. And they're grinding past one another in what's known as a strike slip relationship. So the San Andreas Fault is a strike slip fault where it's dragging past each other. And that's why California looks kind of like this. And if you look at the mountain ranges, you can see the Great Central Valley there. But if you look at the mountain ranges, like we just discussed, you can see that they are not aligned true north, true south. They are aligned more or less northwest, southeast, trending in either direction along the San Andreas Fault. Does that make sense? Okay, that's part of the reason for the uplift of those mountains. But then I also want you to notice these mountains down here. And if you're already paying attention, probably you guys are already way ahead of me. But if you look at that, those mountains aren't oriented northwest, southeast, are they? They're oriented almost deliberately east-west, pretty much a straight line across. They're traversing or transversing the San Andreas Fault Zone, and that's why they're known as the Transverse Ranges. And they're right here in your backyard. You can see them to the north of us every time you go outside. Why are they there? Well, I'd like you to join me in an experiment where you hold your hands together like this person is doing, and then drag one of your hands towards you and push the other one away from you. And what you're going to feel is friction between your two hands. And the more you push, the more friction you're going to feel. right? You're not rubbing them back and forth. You're simply pressing them together and then pulling one hand towards you and pushing the other hand away from you. Now, if you do that long enough and hard enough, eventually you're going to slip, right? And with the San Andreas fault, which is doing the same thing, that slip is when you would have an earthquake, when you have the two plates suddenly grind past each other and release all the built up energy. Now imagine that you've got a scab on one of your hands. As you are pulling one hand towards you and pushing the other hand away from you, what you might feel is that scab starting to peel off, starting to have just a little bit of it start to be dragged in one direction or another because of the pressure you're exerting on it. And that's what happens to chunks of California's mountains as the North American plate and the Pacific plate continue to grind against each other and pull in opposite directions from each other. And occasionally, you have a separation of a minor chunk of that that then reorients itself. And that's what you have with the transverse ranges, where you have a chunk that is kind of pulled sideways on either side of the San Andreas Fault, but that's one of the reasons for the orientation of it. And that's why when you look at these mountains, realize what it is you're seeing, because they're responsible for a lot of the weather patterns that we experience here in Southern California. So again, if you're looking up north and you see those mountains, the San Bernardino Mountains and so on, or the San Gabriel Mountains, realize that they're oriented more or less east-west, and they're doing that as a result of the action of two tectonic plates pulling against each other. And as a consequence of this, they're going to have an effect on weather patterns and air patterns, including a phenomenon you're probably familiar with called the Santa Ana winds. The reason we have Santa Ana winds is because of everything we've just talked about, where in our latitude, as we discussed with those global convection cells, you're going to have, because of our latitude, we're going to have developing high pressure systems in our area where you have that high pressure developing. Because we are in the northern hemisphere, the air is going to rotate in a clockwise fashion, which means some of that air is going to bleed off and be drawn to low pressure systems that are off the coast. And they're going to have to do that by getting through the mountains that we just discussed. So you can imagine the Santa Ana winds coming off that Great Basin cell that you see diagrammatically in the upper right. Clockwise rotation, the winds come down and they aim for Southern California. They come down the hills, which increases speed. They increase airflow as they get to lower elevations. They increase in heat. And then as they start moving through the mountains and moving through the passes and moving through the canyons, that focuses them and narrows them and increases their speed even more. So if you're looking at this diagram of how the Santa Ana winds are coming in off the desert and getting through the mountains, you can see that they're flowing through the various passes that we have in our local mountains. Which mountains, you say? The transverse ranges. You can see that they're more or less east-west oriented, and it's through gaps in them, like Cajon Pass, as one example, that these Santa Ana winds flow that we experience today. And just to follow up on that thought, we may or may not be near the end of fire season. I don't want to say we are and then have a giant fire break out, but when you think about our fire season as we experience it here in California, there have been people who talk about, well, it's the forests, well, it's the underbrush, or people who talk about, well, it's the water availability and so on. A huge factor of it is going to be the Santa Ana winds, and Santa Ana winds are something we cannot control, and they are always going to be there. So even with lots of water, I'm not saying we don't need water to put out fires. I'm not saying we don't need to do better forest and woodland management. What I am saying is even with those actions in play, you are still going to have a constant threat of wildfire, massive wildfire, because unlike other areas of the country, we have Santa Ana winds, and those Santa Ana winds drive these flames and they carry the sparks, and they can be devastating. If you have a massive fire during a Santa Ana wind event, the results can be and have been catastrophic. So that's a little bit about our weather today and our air resources today. Let's go back to looking at the composition of the atmosphere itself. We talked about nitrogen and oxygen and carbon dioxide, but I want to focus now on carbon dioxide as well as methane and water vapor. And I want to focus on those because they are known as greenhouse gases. And again, we're going to be talking about greenhouse gases. I've got a lecture on greenhouse gases coming up later in the term. I think it is after the third midterm, so no worrying about it now. But I want to start touching on this topic now just to give you kind of an entry for it. And in order to understand greenhouse gases, I'd like you to understand greenhouses. And I don't know how many of you may have seen greenhouses or worked with greenhouses or who know how greenhouses work. But essentially, a greenhouse is going to be something like this, where it's a building made of glass or some other material that will allow light to enter. And then what happens? Well, what happens is the energy comes in, but it's not able to escape. Sunlight is able to pass through the glass and warm the plants, and then those plants in the soil, they warm out and they warm up and they radiate heat back out. But that heat is a lower energy kind of energy, a lower intensity kind of energy than the sunlight coming in. And so it no longer has the ability to get back out through the glass to the same extent that sunlight comes in. So you have a continuous buildup of heat inside the greenhouse. Now, for those of you who have ever visited a greenhouse, you know that you step inside and it's going to be far warmer inside than it is outside. That doesn't mean that heat doesn't radiate out. If you stood next to a greenhouse on the outside and leaned against it, you might very well have noticed that it was blazing hot to the touch, and you can actually hurt yourself because heat is making it through. But it's not making it out to the same extent that it's making it in from the sunlight. And so what you have is a net increase in the heat inside this, and that is a consequence of transitioning from light energy to heat energy, and some of it being lost as waste, which is exactly what Isaac Newton was talking about way back when with his principles of thermodynamics. We talked about them before. We're going to talk about them again, but this is why greenhouses work the way they do. It's because of Newton's laws of thermodynamics. The Earth's atmosphere functions in the same way as a greenhouse. Solar radiation can pass through the atmosphere when it's clear. A lot of that is then absorbed by the Earth's atmosphere. So you've got about 25% of the sun's energy that reaches the Earth being captured by the Earth's atmosphere. And that warms the atmosphere, which keeps the surface of the Earth warm. All right. You have another quarter of the energy being reflected back off into space. So 25% absorbed by the atmosphere, 25% reflected by the atmosphere back out into space, which leaves the remaining 50% to be absorbed by the Earth itself, to be absorbed by the land, absorbed by the ocean, absorbed by the plants that are the producers that provide energy for all of the ecosystems, or the vast majority of ecosystems on the planet. All right. Now, that's the energy coming in. Once the Earth, whether it's the land or the ocean, has absorbed some of this energy, some of it is converted into heat and it reflects back out into the atmosphere. That's about 5% of the energy. And that, because it's a lower quality energy, it doesn't have the intensity of direct sunlight, it does not make it back out through the atmosphere. It gets trapped in the atmosphere and continues to warm the atmosphere along with the incoming solar radiation. So that is the greenhouse effect, and that is something that we depend on. We are here on this planet, we are living beings on this planet because of the greenhouse effect. Without it, we simply wouldn't be able to survive. And this is what you see here. Down there in the troposphere, you can see that down where we are at the bottom of the tropospheric level, you can see where it's designated in red down there in that column. That's indicating relatively warm temperatures, the temperatures that we're used to, that we can survive with, and that other living things can survive with as well. It's not like that elsewhere in the solar system. For example, next time the moon is up, feel free to take a look at it and realize that the moon does not have an atmosphere, which means that it does not have a greenhouse effect. So if you're looking at the moon, what you're looking at is naked rock. And when the sunlight is hidden from the moon, which let me see which one I forgot which one goes first, the shadow area or the light area. I'm sorry, but let's just pick one. Yep, that's the shadowed area. Because sunlight doesn't reach the dark half of the moon, and the dark half of the moon changes as the moon moves around the Earth. So there's not a permanently dark side of the moon, irrespective of what Pink Floyd might have said, irrespective of what the TV show Space 99 1999 claimed. There is no permanently dark side of the moon. There is a permanently far side of the moon relative to us that we can't see unless we send somebody up there or send equipment up there. But there is no permanently dark side of the moon. So when the moon turns its face away from the sun, there is no atmosphere there to capture solar radiation and keep things warm. And because space is not good at retaining heat, as soon as this part of the moon rotates towards the dark side, it starts losing the heat that's preserved in the rock. There's no atmosphere to hold it in, and so the temperatures drop to about 280 degrees, negative 280 degrees Fahrenheit. And then the moon keeps turning, and parts of it turn back into the sun. And now there is no atmosphere to protect the moon from the harsh rays of the sun. And that's why on the sunny side of the moon, you can get temperatures in the positive of about 260 degrees Fahrenheit. So you've got a wild shift from negative 280 degrees Fahrenheit to positive 260 degrees Fahrenheit. And that's what it's like if you're exposed to the sun and the darkness out there in the middle of space, unless you have an atmosphere, unless you have a greenhouse effect. And so, again, that's why the greenhouse effect is a good thing. We depend on it for our survival. We wouldn't be here without it. And so, when we went to the moon, we had to kind of bring the greenhouse effect with us in terms of these enclosed suits. And I want you to think for a moment about the technological marvels that these suits are to keep astronauts relatively cool at 260 degrees, but also relatively warm at negative 280 degrees. That's a pretty fancy suit. And so that's one of the things that was accomplished when in the 1960s and early 1970s we were sending astronauts and others to the surface of the moon. All right, so please be aware. I probably won't test you on the actual numbers because, again, we're getting a little too specific. But be aware that it's really, really, really cold on the dark side of the moon. And it's really, really, really hot on the light side of the moon. Now, what do you say about Venus? Venus does have an atmosphere. So what's the difference here? Well, the difference here is that Venus, it's closer to the sun, has a much thicker atmosphere to the point that we have never, with stuff outside of the planet, with telescopes or satellites or anything, seen the surface of Venus because the cloud cover is so thick. And so this is the opposite of what I just talked about. With the moon, there is no greenhouse effect. With Venus, it is a runaway greenhouse effect to the point where the surface temperatures there are about 890 degrees Fahrenheit. And that's because the atmosphere of Venus is doing exactly what I just told you was happening on Earth, but much more intensely because the atmosphere is so much thicker and because Venus is so much closer to the sun and absorbing all that radiation more directly. Now, have we seen the surface of Venus? We have, by landing satellites that actually get through that atmosphere and settle down. These were sent by, I believe, the Soviet Union. And this satellite is one of the few pictures we have of the surface of Venus. And one of the reasons is it's so difficult to get there. And number two, this lander melted after about half an hour. So it was able to take limited pictures and transmit them back to Earth. And we still don't have really good photos of the surface of Venus. We do have radar and LIDAR mapping of the surface, so we do have some idea what the surface looks like. But in terms of actual photographic evidence, that's very hard to obtain because it's so bloody hot on the surface of Venus. Well, what about Mars? Mars is another planet that's it's further from the sun than we are. It's smaller than we are. But people still talk about Mars as potentially a viable candidate for a planet that we might inhabit at some point in the future. between you and me and the wall, I don't think that's going to happen in my lifetime. I'm going to be surprised if we even land people up there in my lifetime, but that's possibly because I am cynical. Nevertheless, this has been discussed as a possible place where people might colonize and live there. And so the temperatures here, which have been determined directly because we can land landers on the surface of Mars and they don't melt from that incredibly intense atmosphere like you see on Venus. The temperatures here range between a high of 70 degrees, maybe up to 75, 80 degrees, which is relatively comfortable, but the lows are down to about a negative 100 degrees Fahrenheit, which is quite chilly. So even here, you would need protection from the elements in order to survive. And the reason is Mars does have an atmosphere, but it is a very, very, very thin atmosphere. And part of that is a consequence of Mars being smaller and not smaller than Earth and not having the gravity that Earth has to help maintain holding some of those gases together. But apparently, Mars is also not tectonically active. The plate tectonics I just discussed with you about the North American plate and the Pacific plate, and they're grinding past each other and so on, that's not happening on Mars. Part of the reason Earth has plate tectonics is because of the Earth's molten outer core, which has its own convection cells that are interacting and creating Earth's magnetic field and also driving the activity we know of as plate tectonics. Apparently, Mars has a mostly solid core that doesn't have the energy that Earth's core has, and so there are no noticeable plate tectonics on the surface of Mars. And so this is part of the reason that we see some of these features, but we don't see the tectonic activity, so that we don't see that changing. And as a consequence, you have the atmosphere being lost. It's not being held in place. What you also have, because of that lack of plate tectonics, is you have no protection from a phenomenon known as the solar wind, where planets in the inner part of the solar system are bombarded with particles from the sun. On the Earth, because we have the convection cells in the Earth's outer core, you have that energy being converted to electrical energy and to magnetic energy, which is generating the Earth's magnetosphere. And that helps reduce the impacts of the solar wind on Earth's atmosphere. That's one of the reasons our atmosphere is here. Mars doesn't have that because it's got a more or less solid core, which means it doesn't have plate tectonics, which means it's not generating that same magnetic field. If humans ever do manage to get to Mars, in addition to managing the heat and the cold and the lack of water, they're also going to have to negotiate somehow that amazingly intense solar wind that is stripping the atmosphere from the planet and causing a lot of damage relative to what we enjoy on Earth. Now, if you are still being clever, if you're already over the whole transverse ranges things and you're looking for something else to be clever about, I just told you that Mars has a thin atmosphere, in part because it doesn't have plate tectonics, right? The magnetosphere is generated by the molten core, which generates plate tectonics. So, in the absence of that molten core, in the absence of plate tectonics, you have no protection from that solar wind. And so, what I hope you're asking yourself and thinking to yourself, well, since Venus has such a thick atmosphere, based on what you just told us, that probably means that Venus does have plate tectonics, right? Because that would be helping prevent the atmosphere by being stripped from the solar wind. And the answer is good job. You are very, very, very clever, and I'm very proud of you, but also wrong because Venus apparently does not have plate tectonics either. And what has happened is that the solar wind has stripped the atmosphere away, but it's stripped the lighter elements of the atmosphere away. And that's one of the reasons that Venus's atmosphere is so dense and so heavy, because it is only the heavier elements of the atmosphere that have been left behind. And so you have that increasingly thick concentration of atmosphere because the solar wind has done what it does for Venus as well as Mars as well as the Earth, and Venus hasn't prevented it with a magnetic defense the way Earth does. It simply has such a thick atmosphere that only the lighter elements have been boiled away. So that's a discussion of the troposphere, which again is where you live your life. And remember, that's where you find weather. So keep that in mind for the exam. Now let's move up a level to the stratosphere. And this is the only other level that I'm going to test you on. Again, if I test you on anything that isn't the troposphere or isn't the stratosphere in terms of questions about the atmosphere, don't worry about it because I'm not going to test you on anything else. Just the troposphere, just the stratosphere, which goes up to about 50 kilometers. And the reason we're going to touch on this, it's a little bit different from the troposphere. Number one, there's no weather up there. In fact, the air is relatively calm, relatively stable. There's not a lot of movement. There's no convection cells and so on. And this is why this is where we find what we talk about as the ozone layer. And the ozone layer is a layer of ozone which helps protect us from incoming ultraviolet radiation. And here's a different diagram. You can see the troposphere down there. You can see the height that is achieved by some passenger jets. And then you can see that massive 40-kilometer thick stratosphere, and above about 20 kilometers above the Earth's surface, that's where the stratosphere, or excuse me, the ozone layer starts. Now, ozone is a variation of oxygen, and essentially, oxygen, the molecule's O2. It is two oxygen atoms that have been binded together. Ozone takes in an additional oxygen atom, so it's O3. That's the chemical composition. And what happens with the ozone layer is that you have solar ultraviolet radiation hitting oxygen molecules and breaking them apart into separate atoms and absorbing the solar radiation. And then you have the appearance of two atoms, isolated atoms. That is the reaction to the absorption of the energy and the transformation of that energy, which is exactly what Newton would have proposed happens because no energy transition or transformation is 100% efficient. And then those oxygen atoms will then bind with oxygen molecules to form ozone, and as a consequence of that binding, they release heat. So the heat that was coming in from the sun as ultraviolet radiation is now released into the rest of the ozone layer. And that is a transformation which is not 100% efficient, which again is exactly what Newton was saying. So, this is how you take incoming radiation and kind of stop it at the boundary of the ozone layer. Not all ultraviolet radiation, some makes it through, but a lot of it does not. This is known as the oxygen ozone cycle. And yes, I am probably going to test you on that, so please be aware of that. But it's how energy coming in is then trapped within the ozone layer. And that's why, if you look at this diagram, there's the stratosphere again, and you realize that the top of the stratosphere, where it's most directly taking in that ultraviolet radiation, is at 0 degrees Celsius. It is way cold, but it's much colder at the bottom of the stratosphere because the solar energy is being trapped at the top of the stratosphere through the cycle that we just discussed. And so you have a temperature gradient in the troposphere where it is warm down here where we're living and cold up at the top. That's why it's so chilly up at Everest, the top of Everest, even the top of our local mountains like San Bernardino, San Jacinto, and so on. But then you move up into the stratosphere and that situation reverses itself. And the coldest part of the stratosphere is at the bottom of that level, and the warmest part is at the top. And that's because of the solar radiation that is incoming and striking the top of the stratosphere. Now, as I mentioned earlier, some ultraviolet radiation, long wave or soft ultraviolet radiation, does make it through the ozone layer. And for those of you who like to work on your summer tans, this is the ultraviolet radiation that you like because this is what's going to help you get a nice tan. There's also ultraviolet B radiation or UVB, and that's a medium wave radiation, and the majority of that is stripped out of the stripped out is bad. Forgive me. The majority of that is absorbed by the ozone layer, so only a small percentage of that makes it through to the Earth's surface. And what you experience there would be sunburn. And then ultraviolet C radiation is shortwave, very hard ultraviolet radiation, and the vast majority of that is blocked by the ozone layer because it can be deadly with prolonged exposure. And just as an aside, for those of you who are traveling, those of you maybe you're going to Ontario International Airport and taking a flight, next time you're on the escalator, take a look at the escalator where it says that it's safe to touch because those rails are being sterilized by ultraviolet C light technology. It's localized ultraviolet radiation produced by this machine that is so strong that it kills any viruses or bacteria that are present on that surface. And so the ultraviolet radiation there is being harnessed to effectively help with human health. The stuff coming through the atmosphere is not healthy at all. Okay. Once again, we get back to the surface of Mars, and because the atmosphere is so thin, it doesn't have that protection from the ultraviolet C radiation. So, in addition to dealing with the lack of oxygen, the relative lack of oxygen, in addition to dealing with the cold temperatures, in addition to dealing with the lack of a magnetosphere and the intense solar wind, you would also have to deal with hugely intense solar radiation, including very harmful UVC radiation on the surface of Mars. Now, another thing to talk about with respect to the ozone is a feature where you actually have what's known as a hole in the ozone. And this is an area that moves around the planet. It waxes and wanes during the course of the year and from year to year. But more or less, it's positioned over the southern hemisphere. And this is where the ozone in the stratosphere has thinned out. And as a consequence, it is letting more and more ultraviolet radiation of all kinds get through to the Earth's surface. And this was proposed as a possibility way back in the journal Nature in 1974, where they were saying that possibly what were known at the time as chlorofluoromethanes were leading to the destruction of the ozone layer. This is a hypothesis that was advanced, and it was so significant a hypothesis that it was published in one of the premier journals of that time, or even today, Nature is a huge journal. And just as an aside, here's another anecdote. I won't keep you too long, but back when I was in high school, there was a book that came out called Lucifer's Hammer about uh, what happens if a comet were to strike the Earth while people are alive. It even takes place largely in Southern California. It's a bit out of date now, but it was a fascinating book at the time. It came out in 1977. And the reason I mention it is because the authors at the time poo pooed this whole idea. One of the characters even referenced it and said it made him want to throw up. In 1977, just a few years after this is published, there are science fiction authors who are known for their scientific veracity who are rejecting this idea out of hand that this could possibly happen. Turns out that the science fiction authors were wrong and the scientists were right, because here's another article from Nature in 1985, a little over a decade later, that now is measuring losses of ozone in Antarctica because of what now are known as chlorofluorocarbons, or CFCs. And so the hypothesis is advanced and published in 1974, and the confirmation that that is happening was published in 1985. Now, again, as we discussed, it remains a hypothesis, but if you want to challenge that hypothesis, you don't just challenge the 1974 paper, you'd have to challenge the 1985 paper and subsequent studies that are still ongoing today. And so the question is, what are the chlorofluorocarbons and where are they coming from and why are they driving this? And the answer is largely human activities, particularly things like early hairsprays, which are producing chlorofluorocarbons that release into the atmosphere. And once they get cycled through the troposphere and make it up into the stratosphere, once they're there, they stay there because there's not a lot of movement in the stratosphere. They don't have the same weather that we have down here. They don't have the same air circulation patterns that we have up here. So once they get up there, they stay there. And as we keep using these hairsprays, which were big in the 40s and 50s and 60s, and there's a lot of us out there, as we keep producing these chlorofluorocarbons, or CFCs, they make it up into the stratosphere and they start destroying the ozone as was hypothesized. Another thing we were doing was air conditioning, which is doing the same thing. You have the advent of air conditioning, and suddenly everybody's happier. Everybody's clearly dressing better from looking at this picture, um, and keeping things cooler. As a consequence of the development and the spread of air conditioning, though, you had more of those CFCs being pumped into the atmosphere, making it up to the stratosphere and essentially destroying the ozone in certain parts of the Earth's atmosphere. That's why the chemical composition of hairspray has changed to eliminate the chlorofluorocarbons. That's why we use different chemicals for air conditioning now than were used back when air conditioning was first introduced, because of the potential harm to the atmosphere from those chemicals. Essentially, what happens, I probably won't hold you to this, but you have chlorine atoms that are being released and they attack ozone molecules and break them into oxygen. The chlorine then joins with the atom to form chlorine monoxide, which prevents it reforming ozone or oxygen. And so, as a consequence, they're disrupting that oxygen ozone cycle that we talked about earlier. So, the way to stop this is to reduce the release of the chlorofluorocarbons, the CFCs, into the Earth's atmosphere. Now, as I've mentioned, the ozone hole is much larger over the southern hemisphere. Things are a little thin in the northern hemisphere, but not nearly so much. And what I want you to think about again is why. Think about the air around you. Let's say you get up and walk to the kitchen, or you walk outside, or you go somewhere, anywhere. Do you leave a hole in the atmosphere behind you? You probably don't. And that's because the air here where we are in the troposphere is moving all the time. Whereas in the stratosphere, the air is not moving too much. And so if you diminish ozone in one localized area, it's going to stay diminished in that area rather than having a general spread out loss of ozone throughout that atmospheric layer. I hope that makes sense. It's because of the nature of the stratosphere to not have a lot of currents, to not have a lot of movement, that you have the development of what's known as an ozone hole, which, as I mentioned, can change through year to year. You can have changes in the intensity and the location, though generally, as you can see here, it's pretty much locally distributed over the southern hemisphere. And as of 2022, and this is still happening today, because we've changed how we use hairspray, and because we've changed what our air conditioning is comprised of, as a consequence, the ozone hole is continuing to be reduced. It's continuing to go down. It's because people noticed what was happening. They developed a hypothesis. They tested the hypothesis. And as a consequence of their results, they've been able to respond, to plan ahead, and to reduce this loss so that as the ozone hole continues to be reduced, it continues to be better at reflecting some of that harmful ultraviolet radiation. Now, I'm about to talk about an old movie, The Wizard of Oz. And so, for those of you who might not have seen it, you might want to turn your head away and you might want to cover your ears because I'm going to reveal a key plot point. Um, but I want to do this in the consequence of what we just talked about because I'm trying to give you a handle to remember when the exam comes up. I don't want to just tell you something. I want to maybe give you a little hook that you can use to remember it. So, for those of you who remember this scene in The Wizard of Oz, in the Emerald City, where the wizard is about to take Dorothy in his balloon, um, he has this balloon because of how he landed in Oz. And he relates this story earlier in the movie, where he says one day, performing spectacular feats of stratospheric skill, never before attempted by civilized man, an unfortunate phenomenon occurred. The balloon failed to return. The wind changed, and the balloon floated down into the heart of this noble city, where I was instantly acclaimed Oz, the first wizard deluxe. Now, based on what you've learned today, you realize when you see him talking about stratospheric levels and talking about the wind changing, that wouldn't have happened. If he'd made it up into the stratosphere, number one, he would have died because the oxygen's so thin. But number two, the wind wouldn't have blown him anywhere because there was no wind to change. There was no wind to blow him. So had he made it up there, or in this part of the movie, had he made it up there with Dorothy, he'd still be up there. And I've been talking about this for several years, and back in 21, one of my students sent me this lovely image representing what it would look like if the Wizard of Oz had been trapped up in the stratosphere. His cold skeletal hands outstretched, just floating pretty much in place. And so I wanted to give you this image, hopefully to help you remember when you get to the exam that there's not a lot of air movement in the stratosphere. It's very cold and very still and very quiet. And if the wizard and Dorothy and Toto too ever made it up there, they'd never have come back down. Now, that's the ozone in the ozone layer in the stratosphere. That's what's known as good ozone. We do have ozone down here in the troposphere. And down here, it is bad ozone. And I'm going to test you on this as well. I want you to remember this because the ozone that we have down here is naturally occurring, and as we've just discussed, it protects us from the sun's ultraviolet radiation. Tropospheric ozone is created by chemical interactions with man made emissions. We generate ozone, but it remains a greenhouse gas. In the stratosphere, it is absorbing radiation, doing the greenhouse thing in reverse, absorbing the incoming radiation from the sun. Here, it acts as a greenhouse gas and it's absorbing energy, reflecting back from the surface of the earth and joining with other greenhouse gases to increase the greenhouse effect that we see down here in the troposphere. So be aware that you've got two different kinds of ozone. The good stuff is up in the stratosphere, the bad stuff is down here in the troposphere with us. And in addition to its actions as greenhouse gas, increased levels of ground ozone can lead to an increase in coughing, scratchy throats, shortness of breath, aggravation of lung diseases, increased frequency of asthma, and so on. So be aware that we have ozone down here in the troposphere as well, but it's not necessarily a good thing, whereas in the stratosphere, it is very much a good thing. And with that, that's the end of this lecture on the atmosphere. We'll pick it up next week when we get back together. But until then, have a good rest of your week. Have a good weekend. And we'll talk to you next Tuesday. Take care. Have a good evening. Good night.